Hi, this is Mark Weitzman. Welcome back to my YouTube channel, Theoretical Physics with Mark Weitzman. Today I want to continue with another problem from David Tong's book on electromagnetism, the second in a series of 10 books that he's writing on theoretical physics. And the book itself does not contain problems, but there are problems that are associated with the book on his website. So the easiest thing to do, I mean, you can print them out, is just type his name in the search bar, David Tong, and then just click on books, then click on the electromagnetism book, and then scroll to the bottom. I can't scroll enough. There's information below this. I don't know why I can't. Anyway, he's got an Appendix C, PDF, vector calculus, integral theorems. If you click on that, you get to his example sheet. So this is really just this video is sort of like a freshman, maybe sophomore if you stretch it, physics problem. Mostly it's just a math problem. But let me make this bigger so you can read it. So the problem is problem 2 over here, and they give you a vector field. These are the Cartesian components of a vector field, and then S is an open surface defined like by these parameters x, y, and z. And then what it wants is use the divergence theorem in cylindrical polar coordinates to evaluate the integral over S of f dot ds. And then it says verify your result by calculating the area integral directly, and it gives you a hint on what you should find for the normal to the area integral, or the surface element, which I'll do. I'm going to do this problem manually, and then I'm going to show you how you can do it in like 5 lines using like Maple or Mathematica. Probably the AI programs would be able to do this also very easily. So what I want to do, let me write down the problem again. This is a vector function. X is the position vector, and F is the field. And this is x cubed plus 3y plus z squared. The second component, the y component, is y cubed, and the z component is x squared plus y squared plus 3z squared. That's our vector field. Our open surface, notice he says open surface, not closed surface. Our open surface is defined by 1 minus z equal x squared plus y squared. 0 is less than or equal to z, is less than or equal to 1. Now in cylindrical coordinates, this would just be 1 minus z, and I will use rho for the radial coordinates, cylindrical coordinates. So rho squared is defined by x squared minus y squared. And if you just graph this, let's say this is rho and this is z, and of course there's another dimension, phi, which goes round. So basically this is just a paraboloid, rotated cylindrical paraboloid. I'm not very good at drawing these things. This is not a zero derivative. But anyway, the surface corresponds to this. It is an open surface. It does not include this line here below. And it wants you to use the divergence theorem to find it. So let's just write use divergence theorem. To find the integral of f dot ds. Okay, so how do we do that? Well, to apply the divergence theorem, we're going to need a closed surface. So I'm going to add this plane, the part of the surface in this plane, which is not part of the original surface. I'm going to add that. Now we have a closed surface. Let's call this S. Let's call this S2. So we have the integral. The divergence theorem tells us that the integral of f dot, I'll put ds plus ds2, because that's the whole closed surface. The integral of that is equal to the integral over the volume of the divergence of f dv. Let me make this clear. Okay. So the strategy is that the integral of f dot ds is equal to the integral over v of the divergence of f dv minus the integral of over ds2, the vector, dot f. Now integrating over this surface will prove to be particularly easy, so that's why this is an easy way of evaluating. I don't understand why this software is just never works. That will be the easy way to evaluate this integral. So let's calculate the divergence of f. This is very easy. The first component only has that x cubed term because we're taking the partial derivative of the first component with respect to x, so we get 3x squared. Second component gives us 3y squared, and then the final component gives us plus 6z. And I will write this in cylindrical coordinates as just 3 rho squared plus 6z. So integrating, this is not a hard integral. Let's do it. We're going to integrate. Z goes from 0 to 1. Phi goes from 0 to dz, 0 to 2 pi. And then the using this relationship, we see that rho goes from 0 to the square root of 1 minus z. And our measure on this volume element is just rho d phi dz. It's well known as the cylindrical measure. And we're going to integrate the divergence, which is 3 rho squared plus 6z. So we could just put this in the y. It's like all of a sudden I need 2 fingers to scroll, when before I could do it with 1 finger. Okay, so let's evaluate this integral. It's not too hard. This phi isn't involved, so that just gives us a 2 pi. The integral from 0 to 1 dz. Now we get rho to the 4th, 3 rho to the 4th over 4, plus 3 rho hold on a second. Yeah, we're integrating with respect to rho, so 3 rho squared. That dot shouldn't be there. Three rho squared z. And both of these things are evaluated at the square root of 1 minus z on the upper limit and 0 on the lower limit. So this is equal to 2 pi, the integral from 0 to 1 of dz. Oh, I have 3/4 1 minus z squared plus 3 1 minus z. So let's integrate that. This is an easy integral. So this is equal to 2 pi. And we're going to get minus 1/4 1 minus z cubed. Because that gives us a minus 3/4. The minus sign from the z gives us 3/4. And we're going to have the square. Plus 3/2 z squared minus z cubed, all evaluated from 0 to 1. So this is equal to 2 pi times 3/2 is equal 1. That's 0. We get 3/2 minus 1 plus, it's equal 0. These two terms vanish and we get plus 1/4, which is equal to 2 pi times 1/2, 1 times 1/4, 2 pi over 4, which is equal to, I think I did that wrong. Definitely did that wrong. Okay, this is 2 pi times 1/2 plus 1/4, 3/4. This is equal to 3 pi over 2. So that's what the divergence theorem gives us by the volume thing. Now let's do the other integral, the bottom surface, the surface integral over S2, the integral of f dot ds2. Now, on dst, the surface ds2, the outward normal is in this direction, and it's just minus z caret. So we only get the third component of the thing there. So this is equal to the integral. Now I have x squared plus y squared plus 3z squared. And it's a minus because we're dotting with minus k caret, so that just gives us the third component. But z is equal to 0 on this surface. So I just have this is just a area integral in the plane. And I'm going to work in polar coordinates in the plane. So it's minus the integral of rho squared dA. Okay, and this is equal to minus the integral from 0 to 2 pi d phi, the integral from 0 to 1, because in the plane rho goes to 1. And then I just have rho squared rho d phi. So this is equal to minus the integral from 0 to 2 pi d phi, the integral from 0 to 1 of rho cubed d rho. This shouldn't be, I already wrote down the phi. Okay, and so this is equal to minus 2 pi, then I have rho cubed, rho to the 4th over 4 from 0 to 1. So this is equal to minus pi over 2. So we add up, so our answer for the integral over ds of f dot ds is equal to 2 pi that we got from the divergence theorem Then I add in this integral, which is plus minus pi over 2 is equal to 3 pi over 2. So that's our answer. Now it asks us to do the integral directly, the surface integral directly, and that's going to be a little bit more involved. So first thing I have to do is we have to determine on the open surface we need to determine as a vector the surface, differential surface. I'll put a vector in it, ds. So first thing we need to do is first thing we should do is we parameterize the surface. And again, I'm always working here. When I put like 3 components, they're always Cartesian components, even if I use rho and phi. So the surface is rho cosine phi, rho sine phi, and 1 minus rho squared. That gives us, remember our definition was we needed to have 1 minus z. So 1 minus rho squared is rho squared. That should be equal to x squared plus y squared, and rho squared cosine squared phi plus rho squared sine squared phi is equal to rho squared, which is x squared plus y squared. So we have the right parameterization. Now, once you have a surface parameterized by 2 parameters here, rho and phi, it's easy to get the normal element, the differential surface area. We just take, first we do with one parameter, the partial of s with respect to rho. This is equal to cosine phi sine phi minus 2 rho. Then we get the second element, partial of s with respect to phi, and this is equal to minus rho sine phi, rho cosine phi, and 0. And now we just take the cross product. So ds is equal to the partial of s with respect to rho, cross, vector cross product in 3 dimensions, the partial of s with respect to phi, d rho, d phi. Rho and phi could be u and v, it could be anything. Notice we don't put in measures, cylindrical measures yet and everything. These are all contained in this cross product. So let's just do this cross product here. Remember, these are Cartesian components. So I have EX, I'm sort of mixing things, EY and EZ. I don't have to, but it's easier to write down. Cosine phi, sine phi, minus 2 rho, minus rho sine phi, rho cosine phi, and 0. D rho, d phi. So this is equal for ds, it's equal to EX. Actually, well, I wrote EX. I'll leave it that way. Sometimes you write X caret and sometimes you... So I'll just write EX times... This is first the 0 and then minus the minus. 2 rho squared cosine phi. This is a vector. Plus EY. These are vectors. EY times 2 rho squared sine phi plus EZ times rho cosine squared phi plus rho sine squared phi, which is just rho. So This is our vector. I'll just write it in terms of components now. And we multiply everything here by d rho d phi. So I write it in components. It's 2 rho cosine phi, 2 rho sine phi, 1 rho d phi. And if we go back to the problem, it does mention that you should find ds is equal to 2 rho cosine phi, 2 rho sine phi, comma 1 rho d phi. So at least we did that part right. So now that I have that vector, it's very easy for me to do f dot ds. Although it's not that easy in an expression, and I'm mixing notation here, but you know how each of these things are defined. Times 2 rho cosine phi, plus y cubed 2 rho sine phi plus x squared plus y squared plus 3z squared. Okay, and all of that is multiplied by rho d phi. Now we substitute our usual, x equal rho cosine phi, y equal rho sine phi, z equals z. And this whole thing is going to multiply out. It starts looking ugly, but it's not going to be that bad. Cosine to the 4th phi plus 6 rho cubed sine phi cosine phi plus 2 1 minus rho squared rho squared cosine phi plus 2 rho to the 5th sine to the 4th phi plus rho cubed plus 3 1 minus rho squared times rho. Remember, on the surface I wrote z equals z, but z is actually, we're on the surface. Okay. So z equal 1 minus rho squared. So now there's a lot of terms here, and this looks bad, but let's see what we can do. First of all, this part over here can be written as like 1/2 sine 2 phi. And whenever you integrate sine 2 phi from 0 to 2 pi, sine phi or sine 2 phi from 0 to 2 pi, it's just 0. So this term is gone. Cosine phi is the same thing. When we integrate that from 0 to 2 pi, that's gone. So I'm now left with these 4 terms. Now, so the integral we want to evaluate is the integral from 0 to 2 pi d phi, the integral from 0 to 1 d rho, 2 rho to the 5 cosine phi to the 4th plus 2 rho to the 5th sine phi to the 4th plus rho cubed plus 3 1 minus rho squared. Hold on 1 second. Squared times rho. So that's the integral that we have to evaluate. Now I'm going to, these are not difficult. One can do this by software, but one can also do this by hand very easily. So let's write cosine to the fourth phi plus sine to the fourth phi. This is equal to cosine squared phi plus sine squared phi squared minus 2 cosine squared phi sine squared phi. Okay. This is equal to 1. Cosine squared plus sine squared is equal to 1. Minus 2 cosine phi sine phi squared. And this is equal to 1 minus 2 sine 2 phi over 2 squared. Remember your trigonometries, which is equal to 1 minus 1/2 sine 2 phi squared. Okay, so that's what this is equal to. Now when we integrate the integral of a sine squared phi over a whole interval, this is equal to 1/2. That's the average value of sine squared phi times the length of the integral, 2 pi. So basically I can replace this. I'm going to still have the integral from 0 to 2 pi of d phi. Now I'm going to have the integral from 0 to 1 d rho. I'm going to have, so I'm working with these two terms here. 2 rho to the 5th. And now I get the 1. And this term is just minus 1/4 because the average value of this is 1/2. Get 1 minus 1/4. Okay. And then I have the other two terms, rho cubed. Now I'll expand out this thing over here. So I get plus 3 rho minus 6 rho cubed plus 3 rho to the 5th. And so that's what I get. This is not too hard to do. I'm just making a point of doing everything by hand. So I get 2 pi, the integral from 0 to 1, rho to the 5th times 9/2 minus 5 rho cubed plus 3 rho d rho. And this is equal to 2 pi times 9 over 6 times 2 minus 5/4 plus 3/2. This is just 1, which is equal to 2 pi. So evaluating our integral directly gives us 2 pi. And somehow I wrote that wrong earlier. I'm doing something wrong here. Let me go back. Go back up here. Okay, so when I did the divergence thing, I got 3 pi over 2 for the divergence thing. And then I said what I want to do is do the divergence integral minus the integral over ds2. So I messed that up. So this should have been 3 pi over 2. And this should have been a minus pi over 2. And that's wrong, and this is equal to 2 pi. Sorry about that. So, and doing it directly as we just did, we get 2 pi also. So that's the manual solution. And now I'll just show you how to use software to do this. Much easier. So with software, what we do is we use a package. Now, you might not be familiar with all the packages and everything, and I rarely use Maple, so I always have to go to the help. So when the program's launched, you go to the help menu, and in the help menu, when you launch it, it has like getting started. Here I just want to go to mathematics. Sometimes I want to go to physics. There's a lot of things I can do in physics. And then I just go to vector calculus. I'm sorry, mathematics. I go down here to vector calculus, and I just look at the overview. And this will have an overview of the vector calculus problem. It will list all the commands and things. And then it will give you some examples. So for instance, here I see flux, sphere, so on. I don't remember all the syntax or anything, but I'm going to look at flux. So I go back here on the left side, and I'm going to look for the flux. And now it will tell me exactly how to use flux, and it will give me, much more information than I want. I usually just go to the examples. From the examples, you can figure everything out. So let me go back to this Maple thing. And so I load the vector calculus package, and these are all the commands in the vector calculus package. You can, if you want, just use like a colon here, and they won't show up. So, but I like to see them sometimes, so especially. So now I notice that there's a command vector field. So the first thing I do is I just define my vector field, and I might look up the syntax, but the syntax is fairly easy. Its vector field is like a function. You put parentheses for functions, and then you put the three components in brackets: x cubed, 3y plus z squared. We had these in the definition of the problem. Then you want to tell it that this is a Cartesian vector, and you're naming the Cartesian coordinates x, y, and z. You don't have to use x, y, and z. You could use like u, v, w if you want. So then when you hit enter, it shows you the vector field is this times the, it uses an e bar, but ex, that times ey, and that times ez. Now you can easily, and I use palettes for most of my things, like if you go through the palette like common symbol, you can see that del symbol. So I just hit del.f. I could write out divergence. I could go over here and just write this out, divergence parentheses f. But I use del.f. And so it gives me the divergence. And then I just use the integral. Again, I use these palettes and then fill them in. So it's the integral from 0 to 2 pi of d phi, the integral from 0 to 1 of dz, the integral 0 square root 1 minus z, and then it's the divergence. I wrote it as 3 rho squared plus 6z times the measure rho. And so this is the same thing that I did earlier by hand, and I get 3 pi over 2. Now I go to the flux, and I basically just ask for the flux, and if I look at that help page, it tells me put the vector field you want, that's f, and then define your surface. This is where I had a little tricky, and I had to define it right. But I'm going to use Cartesian components. I know the problem said use cylindrical, but it's easier in software to do this with Cartesian. And I give the components of the surface, which is just xy, 1 minus x squared minus y squared. And xy is defined by a circle at the origin 0, 0 of radius 1. So I hit enter, and it gives me right away the answer, 2 pi. Now, if I want to do the one on the surface as well, which so easy to do by hand, I do the vector field f. Now the surface is just xy comma 0, and xy is in that circle, and it gives me pi over 2. Now, of course, it doesn't know that this surface here is like the boundary, and the outer normal is in the negative direction. So it doesn't know that I really want minus pi over 2 here. But the divergence minus this surface, and this would be minus pi over 2, will equal 2 pi. And so that's all I wanted to do here. It was not a difficult problem, but it's something that, beginning students often don't do correctly, or they mess up in some way. So I just want to do basically what is a math problem, but in physics you'll need this every now and then, at least in first and second year physics. Okay, so I will see you next time. I'm going to do another short video on electromagnetism, illustrating another example of a superposition. Thank you for watching. Bye-bye.